And this is 4-1, the alpha lesson. Okay. So if we look at the learning objectives on the top, solve problems involving optimization, like where something has a max value or min value. And here's a problem from the end. This is 47 at the end of the section. Which of the following values is the absolute maximum of the function? Now, what do you know about f of x looking at that? What kind of shape does that curve have, Anna? What about the problem? Very good. It's opening down. This is not in standard form. Ready? It's 4x plus a negative x squared. So if you rewrote that, that would really be negative x squared plus 4x plus 6. Yes? And because the leading coefficient's negative, and at second degree, it's a problem that's opening down. Does it make sense to you that what you're looking for would be the height of the parabola, the maximum height, except not over the entire domain, they say between 0 and 4 only. So what's the issue? You've done these problems before. You did them in Algebra 2. But now we're asking you to do them without a calculator. Except we can do that already. Here's what's going to happen. In May, you get 2 minutes to answer a question without a calculator. I've been thinking about what the College Board's going to do. I have no idea. But if they go to a typical test, it's 2 minutes for a multiple choice without a calculator, 3 minutes with a calculator. That sound backwards? Yeah, I like my calculator. They're giving you more time to answer the question with the calculator, which tells you what? That's how much more challenging those questions are. So you have 2 minutes to answer this question, and then we will, here we go, begin. Okay, that's it. Ready? Give the answer? Give me the answer. Who cares? I want you to look up here at this work and see how closely your work matches what you're expecting to do. But if you think that's kind of stressful, sitting here and me timing and giving you 2 minutes to answer this question, you have no idea what major is. That's stress. So, ready? This was the question. There's the derivative. What happens? The derivative equals 0 when x is 2. and then the height of the graph would be 10. Here it is if we use the calculator to confirm the answer. You don't need this row. You say, okay, x equals 2. Then what? Well, let's put another number in there. Let's look over here and build an H chart for the problem. So my H chart looks like this. X, half of x, so I'm not going to write that. So. And then dy dx, or f prime of x, what do you want to do? And our work is telling us that at 2, the derivative is 0. You got it? But I do want to write out the derivative, which is 4 plus negative 2x. So that's 0, which means what? Well, that might be a maximum of the graph. It has a horizontal asymptote. But we have to confirm that. So we put another number in here. So let's put 1 in here. If I put 1 in here, you get 4 take away 2. Do 2. If I put 3 in here, I get 4 take away 6, I get a negative 2. What's happening here? At 1, I don't even care what the value of the function is. At 1, the derivative is positive, which means the parent graph is going up. At 2, derivative 0. Horizontal asymptote. At 3, the derivative is negative, which means the parent graph is going down. So in between when the parent graph is going up and going down, we necessarily had the maximum value on the interval between 0 and 4. Yes? How about the answer? How about the restrictions weren't on there between 0 and 4? Did that change your answer? How do I know what's happening when the derivative is 100? Negative 50. Right? The derivative is linear. It's only going to have 1 0. Okay? So, if C in the function is a local max or a local min, that inverted V is a, or that V is a 4. So 2 is the C in this, in that problem 2 is the C. Then the derivative at C is 0 or fails to exist, does not exist. Okay? However, you have to be aware of the converse error. You cannot take what's in front of if and what's in front of then and exchange them. If the derivative at C equals 0 or fails to exist, then it's a local max or local min. False. We don't do logic anymore in pre-calc. We used to. You cannot take what's in front of the if, in front of the then, and switch them. It's a one-way street. So it's saying this. If you know you have a local max or min, then that's confirming the derivative is 0 or fails to exist. Here, what did we do? We found the 0. But then we also went either side of that 0, either side of that value that made it 0. This was the C in the problem. We went to 1 and 3 to confirm the behavior of the derivative, which you need to do. So let's go to example 3. Wrong page. I mean, there's some things in the book on page 188. Let's go there first. There's some pictures in the book in the margin. Ready? And they say, you've got this, they're focused on y equals x squared, which is a great idea because that's a number 2 user-friendly parent group. They say, look at these intervals. From negative infinity to infinity, and infinity always gets parentheses. There's no absolute maximum. It's just going through the ceiling. The absolute min is there. How about if they said 0 to 2 with brackets, which is inclusive, closed circle. Then from 0 to 2, the maximum occurs at 2, and the minimum occurs at 0. In the third picture, you have an open circle at the origin, so there is no min, because 0 isn't part of the set. Closed circle at 2, so that's the max. 0 and 2, open interval, no max nor min, because you have 2 open circles there. So that's, I don't want to be presumptuous about that. But that table on page 188 goes with those 4 pictures in the margin. You have to be careful about what's included in the domain and what's excluded. So back to example 3. We have y equals x to the 2/3 power. And if you look on page 190, there's a picture in your book. Remember, we referred to this back in the beginning of chapter 3 as a cusp. You are not accountable for that vocabulary word, but you've seen a picture like that. Okay? And the question says, find the absolute max and minimum on this interval. -2 to 3 inclusive. Right? What do we do? We take the derivative. And the derivative, I mean, the parent graph would be that. We're going to edit this table. And we have x to the 2/3 power. The derivative would be 2/3 x to the -1/3. What's that? Yes, which equals 2 over 3 times the cube root of x. You're rewriting the radical. So what happens? At 0, the derivative does not exist. Because the square root of 0 is 0. 3 times 0 is 0. You can't evaluate 2 divided by 0. So the derivative never equals 0. Never equals 0 because for a fraction to be equal to 0, you have to have 0 on the top of the fraction. So the derivative doesn't equal 0, but it fails to exist at this value. So then what? I backed up to -1 right here in the table. If you put -1 into that derivative, yes? The cube root of -1 is a -1. So the answer would be negative. I don't care about the value. It's negative. Without looking at the picture in the book, that's telling you the parent graph is falling. Now we go to the other side. We go to a 1. The derivative will be positive. The parent graph is rising. So necessarily, 0 is the minimum value. You put 0 in the function, you get a 0 without looking at the picture in the book. That's going to be the minimum value. Not the maximum value. We have a closed interval, -2 to 3. So those endpoints count. So if I put -2 in the function, I get the cube root of 4. Yes? If I put 3 in the function, I get the cube root of 9. So this is the maximum of the graph. The picture of the book is only there to help you confirm what you're doing analytically. And if you think back on this, you did a lot of these problems in Algebra 2, maybe the beginning of pre-calc, using second trace min, second trace maps. And what you're being asked to do now is do the same type of problem without the technology. It goes to your depth of understanding. Right? We're going to leave that up there. You're going to go to problem 11, please. Okay. So 11. So don't worry about the picture at the top. I mean, that's just to confirm the answer. What are we doing? Here's the derivatives. Negative x to the negative second, which is the same thing as negative 1 over x squared. The derivative of ln x, 1 over x. This is an addition problem. So I'm going to add these. I multiplied 1 over x by 1 in the form of x over x out of a common denominator. And you get x take away 1 over x squared. That's the derivative. That's just algebra. Multiply by 1 so you can add the fractions. So what happens? 1 makes the derivative 0 because 1 makes the numerator 0. What makes the graph undefined? What makes the derivative undefined? Hello? Wait. 0. So why don't we have 0 in there? Correct. Look at the domain restriction in the question. They want to know for problem 11, you got to pay attention to this or you're going to spin your wheels and do unnecessary work. From 1/2 to 4. So now what? I back up. I went to 0.5 and 1.5. What happened? The derivative was negative and it went to positive. So therefore, at the 0.11 has to be the minimum. Where's the maximum? I compared the outputs. And the output at 4 is higher than the output at 0.5. Because what's happening? Here the derivative is positive, yes? It's telling you the period graph's going up. Well, if there's no more zeros in there, it didn't turn around, even if you're not looking at it. So you just go to the end point, which is included. You don't have to worry about the graph changing direction in between. Because it would have to be, the derivative would have to be 0 or fail to exist. And it's not going to have another 0 because the numerator is linear. And it's not going to fail to exist because that value is not in the window. Okay? So, we are going to go to the next example, and it's an open interval. I'm going to go to the book. I think I lost this picture. And what's going to happen is we're all going to go over example number 4, and then the children who are at home are going to be dismissed to do the exit ticket, and the children that are here are going to go do the problem. It's referenced in these. You good? So here's the picture. And it says, find the extreme values of this. Y equals 1 divided by the square root of 4 take away x squared. Here's the picture. Well, I don't really care. I could do this without the picture, but it's kind of helpful when you first start doing it. So let's do this one. So here's the derivative. On page 191. How they do that? It's chain rule, it's going to help you for your assessment. They rewrote it as 4 plus a negative x squared in parentheses raised to the negative 1/2 power. Make sense? Hopefully. Power rule, the derivative will be negative 1/2 mu to the negative 3/2 times d mu. The derivative of what's inside the parentheses, which would be a negative 2x. 0 subtract 2x. The negatives would reduce, the 2's would reduce. You would get x over mu to the 3/2 power. So what's happening? At 0, the numerator is 0, so the derivative fails to exist. Yes. I'm sorry, the derivative is 0. When does the derivative fail to exist? If you put a 2 in here, you'd have 4 subtract 2 squared, or negative 2 squared. But those values aren't in the domain. Because 2 and negative 2 make the parent graph fail to exist. You have an open interval. Okay? So what's happening? You put a 0, makes the derivative 0, and you test points on either side of the 0. And you will see the graph is falling towards the 0 when x is 0, and then rising as you leave from there. Because it's an open interval, there are no maxima. Okay? So we're going to send you to a problem that has an open interval. It's 25. So we're going to pause this. The derivative of the parent graph would be x over 1 take away x squared to the 3/2. The same, essentially the same thing. You put a 0 in here. A 0 makes the numerator 0. What's going on? It's an open interval from -1 to 1 for the parent graph. The graph can't take on the values 1 or -1, because that would make the parent graph, would make the denominator 0. So I go over here a little to the left, a little to the right. I put a -1/2 and +1/2 in here. What's happening? The denominator, you're squaring the input. So the denominator is going to be positive, but the numerator is negative. A negative divided by a positive is a negative. So the parent graph's falling. Put a +1/2 in there, and you get a positive divided by a positive. The derivative is positive. So it's increasing away from the point 0, 1. 0 makes the height of the graph 1. It makes the derivative 0. But that point 0, 1 has to be the minimum on the graph, because to the left of it, the derivative was negative, so the parent graph is falling. And to the right of it, the derivative is positive, which indicates the parent graph is rising. Okay? So that's that for 4-1.